Alrighty guys, so in this lecture we're going to be talking about something called polyatomic ions, but before we get into that, let's do a little quick review of how to draw covalent compounds. So when you have a structure like this, CH2NH, you're going to notice that the H's are split up. There are three different H's in this molecule, but they're split up. That means they're most likely going to be connected to the atom that's in front of it. So we have CH2, that means these two H's are most likely going to be connected with that C, and then we have NH, which means that the H is most likely going to be connected with that N. So when we draw the structure for this, first thing that we want to do is we want to count up how many total valence electrons there are. Okay, so if we have carbon, we're going to count the boxes to carbon. Carbon is 1, 2, 3, 4. That means carbon brings 4 valence electrons to the table. We have H2. That means that every hydrogen has 1, but there's 2 of them, so it's plus 2. If we count the boxes till we get to nitrogen, it's 1 past carbon, so it's 5. So plus 5. And then lastly, we have an H by itself, so it'll be plus 1. So if we add all that up, that tells us how many total valence electrons we have to work with. So we have 4 plus 2, 6, plus 5, 11, plus 1, so we have 12 valence electrons. Now we said earlier that the H's are most likely going to be connected with the atoms in front of them. So when we start planning out our structure, what we're going to be doing is we're going to be organizing them with the H's very close to the atom that's in front of it. So we know that H's always like to be on the outside. So I'm going to put these two H's towards the outside. We know carbon is usually in the middle, so we'll put carbon there, and then we'll just draw the N next to it, and we know H likes to be on the outside, so we're going to put the H right there. Okay, we also know that every single atom in a molecule needs to be connected, so I'm just going to connect, 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 just so everything is connected together to make one structure. Now we have to count how many electrons we use just to connect everything. So here we have 2, 4, 6, 8. That means we used 8 in order to connect everything, so 12 minus 8 is 4. That means we have 4 valence electrons to work with, and we also need to make sure that everything is following the octet rule. Okay, octet rule means that all the atoms need 8. So if we take a look at the carbon, carbon does not have 8. Carbon only has 1, 2, 3 lines, which means that it has 6. So carbon has 6. That means that this carbon right here needs 2. If we take a look at this nitrogen, we notice that it also doesn't have 8. It only has 1, 2 lines, which means that it needs 4. Because it also wants 8. Okay, and the hydrogens are all good because all the hydrogens have 1 line connected to them, and each line is 2, and since there's a line, all the hydrogens are good to go. Alright, so that means that carbon needs 2 more, and nitrogen needs 4 more, but we only have 4 valence electrons to work with. So what we cannot do is we cannot just put the 4 electrons we have left on one of the atoms, because then we won't have any electrons to work with. So here we're going to have to work with a double bond. So since they both need electrons, one thing we can do is just make a double bond like this. If we create a double bond, that means that carbon gains 2, because if you take a look at this carbon, now it has 4 lines connected to it. Since it has 4 lines connected to it, it's going to have 8, so carbon doesn't need any more. And this nitrogen now has 1, 2, 3 lines. That means it only needs 2 more because it has 6. Okay, and we used 2 to make that double bond, so we have 2 valence electrons left, which is perfect because nitrogen needs 2 more. And there you go. That's going to be your structure for CH2NH. Now, if we want to count up how many bonds there are, you're going to see there's a single line here. That's 1, 2, 3. That means there are going to be 3 single bonds. And then, right here, we have 2 lines between the same atom. That means we're going to have 1 double bond. Okay, so this structure right here has 3 singles and 1 double. Alright, so hopefully that was a good review. Now we're going to move on to talking about the structure of a very specific type of molecules. Now this type of molecules, you guys can probably tell by the title of this lecture, are molecules called polyatomic ions. Now we know what ions are. Ions are atoms with a charge. They're charged atoms. Okay, so we know that charged atoms, there are going to be things that have a positive or negative next to them. So we have like Ca2 plus, that means it has a +2 charge, or F minus, that means it has a -1 charge. So that's what an ion is. Now poly is a prefix that means many. It means many. Atomic means obviously atoms. So that means that these are many atom charged atoms. So they're ions that are made of more than one atom. Okay, so another definition, I guess a better one here wouldn't be many, it'd be more than one. So I'll just put 1 plus. Okay, so ions, charged, not atoms now, particles that have more than one atom. So we're not just using Ca2 plus or F minus anymore. We're going to have things like this, SO4 2 minus. It's a molecule, so we have a molecule SO4, and this whole thing, when they come together, they have a negative charge. Now, we basically do the exact same thing when we draw the structure of this. First, we're going to count the valence electrons. So if we look at S on the periodic table, S is on box number 1, 2, 3, 4, 5, 6. So that means S, sulfur, brings 6 valence electrons. Oxygen is also on the 6th box, but there's 4 of them, so 4 times 6 is 24, so 6 plus 24. But there is a -2 charge. We know that electrons are negative, and so if we have a negative charge, that means we have more electrons than we do have protons. So when you see that negative sign, that means we also add 2 valence electrons. Okay, so if you see a polyatomic ion, right? So let me just write Pi, polyatomic ion, and it has a 3 minus charge. That means you're going to have to add 3 electrons to your valence electron total. Okay, but if you had a polyatomic ion with a 2 plus charge, that means you're going to have to subtract 2 electrons. Okay, so just look for the charges are very easy to work with. We've done these before. The charges basically just tell you, are you going to add electrons at the end or subtract electrons? In the case of this problem, SO4 2 minus, since it's a negative charge and we know electrons are negative, you're going to add 2 electrons. So that means in this molecule, we're going to be working with 32 valence electrons. Okay, so again, these are very simple. It's exactly the same as what we've been doing. You just need to make sure you add or subtract the correct number of valence electrons based on the charge. Okay? All right. So when we draw these polyatomic ions, we follow the exact same rules. If you look at S and you look at O, we need to figure out which molecule or which element wants to go into the middle. We know that electronegative ones tend to be on the outside. And so if you look for the more electronegative ones, we go up and to the right. So that means that oxygen, since it's higher than sulfur, is going to be more electronegative. Since it's more electronegative, it'll tend to be on the outside. So we'll put S in the middle and we'll put O on the outside. Now, we know that they all need to be connected together, so we're just going to use some electrons to connect everything together. So we use 2, 4, 6, 8. That means we don't have 32 anymore. We're going to have 24. Okay? Now, we know that oxygen always follows the octet rule. So the octet rule tells us that everything needs at least 8. Okay, but we also do know that S is one of the exceptions to the octet rule, and so S can hold either 8, 10, or 12. So what we need to do is make sure all the oxygens have 8. They have to have 8. But sulfur can hold either 8, 10, or 12. Now, we have 24 valence electrons left to go, or left to use. That means that we can put 1, 2, 3, 4, 5, 6 on this oxygen. If we use 6 for that, and we put another 6 here, we have 12. We have 18. And then we have 24. So we can use all 24 by putting the electrons all on the oxygens. And we're good to go because this oxygen has 8. This oxygen has 8. This has 8. This also has 8. Okay, but there are different ways that you can do this problem. We said that sulfur can hold 8, 10, or 12. That means one other thing we can do is we can actually create a double bond between one of the oxygens and sulfur to create a structure that looks like this. Okay, because here we have in the first drawing we have sulfur with 8 valence electrons. Here we have sulfur with 10 valence electrons. Okay, so this is another way that you can do it. You can make sulfur have 10 valence electrons. But another way you can do it is actually you can create another double bond between one of the sulfurs and oxygens to give it 12 valence electrons. Okay, so this just goes to show you there are multiple ways to do this. We're not going to talk about why yet. We'll get to this later. But this one right here is actually the most correct answer. But we haven't discussed that yet, and we'll get to that later. But this works where we have sulfur having 8. This works where we have sulfur having 12. We can also draw it with sulfur having 10.